Hello, my name is Dr. John Thompson. I'm president and founder of extraktLAB, and today we're going to be talking about CO2 versus ethanol. We're going to be comparing operating costs for both of the techniques and seeing which one wins. So let's get started. When people talk about operating costs, sometimes they confuse it and they conflate it with equipment costs. This is a plot here or a graph. Sometimes when people want to compare techniques, they will look at the equipment costs and they'll look at the operating costs separately. And sometimes it's really hard to really pull those apart and look at them separately because they will impact your operations and your profitability separately. So this table here shows equipment and startup costs for comparing a 1 ton per day facility at 5,000 square feet extraction. It's a startup operation. It's assuming that the throughputs of both CO2 extraction and ethanol extraction are the same. It also assumes the same amount of space being occupied. So we're holding that constant as our comparison metric. And you can see right here, the table shows that, like with the first line, the approximate equipment cost for ethanol is right around $2 million for a setup, as opposed to CO2, which will be right around $4 million. So obviously the CO2 extraction costs more from the equipment standpoint. From the infrastructure standpoint, however, if you're going to have a 1 ton per day facility, you're very, very likely going to exceed the limits for an F2 occupation. It's going to put you into an H2 or an H1 or an H3 occupancy. There's building requirements that are added on top of a normal F2 occupancy. And those building square foot costs are published all around the United States. They vary from jurisdiction to jurisdiction. It ranges anywhere from the 180s I've seen the lowest all the way up to mid to high 200s for H2 occupancy, as opposed to F2 occupancy. There's a lot of inventory actually that's on the market that is F2 occupancy, so it's relatively simple to find that kind of occupancy. But if you're going to build it brand new, we're comparing apples to apples here, it'd be $68 a square foot. So it would cost you a lot less in infrastructure. However, you're still not out of the bag because you still have CO2 as being more expensive. And then you have the solvent startup costs. Of course, with this ethanol setup here, you have to charge it up with ethanol. You have to have ethanol on hand in order to really make that work. And if you're going to charge it up, it's about $15,000 for that. For CO2 to charge up in a 1 ton per day, it's about $115. That's basically because CO2 is so inexpensive compared to ethanol. And you are going to need $2,500 for ethanol for winterization purposes. So you might have a little bit of a startup advantage here for CO2 in terms of costs. Maybe $13,000, pretty negligible. So if you add all that up, the ethanol startup costs are $1.2 million less. So the idea that ethanol setup is less capital intensive is absolutely correct. It is less capital intensive. But that's not the end of the story. It's not a checkmate. It's not a game over. It's not quite that way. Let's continue to dig into this and really see what you're getting in terms of operating costs so you can really make an educated comparison. So is it really game over? Is the checkmate really done? Has ethanol won the day? Let's take a look at some of the other factors, specifically operating costs, that really show that CO2 is a superior technique and will build value for your organization over time. This is a plot, operating cost as a function of the two different techniques. You can see what we're comparing energy cost, labor, testing costs, cost of solvent changeover, and loss of solvent for ethanol here and for CO2 here. And you can see that one of the major striking features of this plot is that CO2 is so low on the operating costs compared to ethanol. And what we're going to do is we're going to go through each one of these factors and we're going to compare ethanol and CO2. We're going to compare the costs for a 1 ton per day facility for CO2 and a 1 ton per day facility for ethanol. And you guys can make your choice after we get done. So let's get started. Here's a plot of operating costs. It's a comparison between CO2 and ethanol as a function of time. The blue is CO2, the orange is ethanol. I'm also comparing food grade ethanol and the cost for food grade ethanol versus denatured ethanol and the cost for denatured ethanol. One of the features of this plot is it's taking into account the startup costs. So you can see that CO2 starts at a much higher cost, initial cost, than does ethanol. So it's taking into account that starting cost. And then it is taking into account the operating costs every month, the cumulative operating costs every month, and comparing them. Now, there are a couple different features of the plot that are important. Number one is the slope. The slope is the cost per unit time. Number two is this crossover point here. This is the point at which this technique here is equal to the cost of this technique here. So this is the point at which there's a crossover and the techniques, including the starting costs, are equal. What this plot is really showing then is that if you have two setups, one ethanol and one CO2, and they're starting off at 1 ton per day and they operate for 3 months, there'll be a point in time that the operating costs for the ethanol catch up to the initial cost outlay of the CO2, somewhere at 3 months, in fact. And after that time, then CO2 has a great cost advantage compared to ethanol. Now, this is for food grade ethanol, and we're assuming $16 per gallon. That's a normal food grade ethanol cost. If you use denatured ethanol, some people do that to lower the costs. You can see that the slope is changing a little bit here. This is the denatured ethanol cost. And so what happens is it moves the crossover time from 3 months to, say, 5 months approximately. But you still have this cost differential advantage over time for the CO2. Now, what we're going to do in the next couple slides is we're going to go through all the assumptions associated with these plots. We're going to take some of the assumptions out and replot them and show you that CO2 has an advantage no matter what you assume. And this all really goes back to the cost of the solvent itself. CO2 is extremely inexpensive compared to ethanol. You're talking about 4 or 5 cents a pound for CO2 typically. And then ethanol, for food grade, $16 per gallon. Okay. So it's just a lot more expensive, period. What we're going to focus on first here is the solvent loss. You can see what we're comparing here is this blue section here, cumulative solvent loss per month, as opposed to this blue section here, cumulative solvent loss per month. You can see that the numbers are quite a bit different, 236 versus 14,000. So let's kind of unpack that. So what we have here on the bottom are two tables. One table is explaining the ethanol loss, and then the second table is explaining the CO2 loss. The ethanol loss is calculated with these assumptions. First is that you're using 30 gallons per cycle, 1 gallon per cycle, 1 gallon per pound dry mass. That's a typical ratio of the amount of ethanol that's required. So if you have 30 pounds of dry biomass per cycle, you're going to need 30 gallons per cycle. If you have 10% loss, that's 2.99 gallons of cycle per loss. It's $16 per gallon. That's the price currently on the market right now is about $30 for ethanol, just because it's not available so much in the market right now. But that price will probably go back down to about 16. And so your cost per cycle is about 87. You have 55 of these cycles per day to make up 1 ton, and you got 3 machines. That's $7,899 per day. As opposed to CO2, these are real numbers, and these are real numbers as well. They come directly from a ethanol equipment manufacturer, and this is the assumption that we're making here. This comes directly from our operations. 22 pounds per cycle, 4 cents per pound, 88 cents a cost per cycle. It's 211 cost per day. That's the difference between costs for the two different techniques per day in solvent loss. It's quite striking. You may say, okay, look, well, I'm going to use denatured ethanol instead and take that cost in half. You can just take this cost and bring it in half. Actually, it doesn't matter. Yeah, because you see from here, the slope is still significant. All you're really doing is delaying the crossover time by a couple months. So one thing that a lot of people ask is, well, CO2 extraction needs ethanol anyway, so what's the point of doing CO2? Well, I think that the graphs that we just talked about should have a real big impact on this. And that is, cold ethanol may be used to help remove waxes during CO2 extraction. That's called winterization. This is the case, no question about it. You can avoid that altogether using low pressure CO2 methods, but you're trading off throughput for that. So if you want to do high throughput, then you're going to be getting those waxes. Here's the key point. Ethanol usage is at least 22x less per cycle compared to ethanol extraction. Yes, you are getting those losses. You're getting the same losses for ethanol, but you're just using a lot less. So those costs are really negligible. Food grade ethanol is used to avoid chemical contaminants. And then ethanol reuse is still subject to FDA GMP practice for changeout validation and specification requirements. So those are the things associated with ethanol. The answer to the question, yes, ethanol is used in winterization, but you don't use much. So it doesn't have a huge cost impact. Now let's talk about cost of solvent changeover. What we are comparing here is this cost, this orange cost, and the lack of an orange cost here. The reason that there's no orange cost here is because with CO2, you don't necessarily recycle it the way you would ethanol. Ethanol needs to be recycled and reused, and there are costs associated with that. What is solvent changeover? That's the first question. Solvents build up contaminants in them as you use them and as you use them for extraction, and therefore they can't be used indefinitely, and they need to be periodically changed out because they get gunky. The solvent changeover is the act of discarding a heavily contaminated ethanol in favor of ethanol that can conform to input specifications. And CO2 does not have a solvent changeover cost because you don't do it. So there are requirements for the reuse of solvents as per FDA guidance. They published, the FDA did a guidance on industry, drug, substance, chemistry, manufacturing controls information. And in there, they give guidance for the reuse of solvents in a manufacturing process. Solvents can be reused, but must be brought back to the original state or made suitable for reuse. And when they say made suitable, they're talking about comparison to original specifications. So the guidance is pretty explicit about the requirements. You have to have a specification. So if you have food grade ethanol, it has to, the specification is suitable for the solvent. So you have to have some accept criteria, a description, and test criteria for that. And then you also have to test it. So if you're going to reuse it, you recover it, then you test it, show that it is perfectly fine. And then you need to collect the data on the impurities that are in there, that are building up over time. And you also are required to submit data on the maximum number of times a solvent can be recycled. So that's the guidance. It's non-binding, but when the FDA comes in and inspects your facility, they're going to be looking at, okay, solvent reuse operations, and does it comply with the guidance? We know that if you don't have any of this information, you're pretty much going to be dinged on it. The other thing is that most people don't, for example, test and retest to check it out. You can validate your reuse operations if it always is coming back again and again and again to the same original specifications. What you can do is document a validation program and say, okay, this process is now validated and I wouldn't expect to have any variance from that, and I'll do periodic testing. So you don't necessarily have to test every batch, but that's how normally it's done. So that is the requirements for solvent changeover. Now, why do you need to do any kind of solvent recovery anyway? Well, ethanol is pretty expensive, so you want to be able to recover it. What this is showing is that as you increase the number of times you reuse it, you're actually increasing the amount of contaminants or other compounds that are dissolved in it. The first plot here shows concentric circles. The first inner circle is the starting ethanol. Now, in this case, I'm looking at ethanol. It's a denatured ethanol. So here you have a denaturant is in gray, and then there's always a little bit of water, less than 1%, or there's some specification on water. Okay, so you have water, denaturant plus ethanol. Then when you use it and you extract, you get ethanol plus a denaturant plus some other stuff that you're dissolving that is not cannabinoids. It may be waxes, it may be fats, it could be pesticides, it could be anything. And then you get all that water that was also in the biomass. That's also now being dissolved and being brought into the ethanol. And then you have cannabinoids here. So that's really what you are getting after extraction. Now, then you need to remove all of the ethanol and you need to remove all of the denaturants. And so that's that final circle here. So this is after recovery of all of that. Now you can see here, you're getting the denaturants here. Oftentimes, and if you do measurements on this, you will pretty much demonstrate to yourself that there's always other stuff left in the ethanol after you distill it. And as you continue the cycles, that amount of other is going to grow and grow and grow. And so that's really what the FDA is talking about. They want to make sure that you have a maximum number of cycles that you use a particular lot of solvent. And also they want to make sure that you're not, like, for example, mixing lots of solvents, lot 1 and lot 2, without validating those lots as being equal. There is a testing requirement, whether you like it or not. You're going to have to test some things and you're going to have to establish how long you can use these solvents. And this goes for CO2 extractors and it also goes for ethanol extractors. So it doesn't matter which one you're doing, but there's a cost associated with this. And if you have a certain number of cycles, you're going to have to switch it out. The deal is that if you have to switch out ethanol and you have 22 times more of it, your cost for switching out is definitely 22x. So that's something to keep in mind. Now let's just get into some of the numbers. Here's solvent reuse cost versus interval time. And what we've done is we've modeled 2 different solvent changeover costs for a 1 ton per day facility for 5 days and 20 days. And it could be 40 days or it could be 100 days, whatever you guys really measure and validate as being acceptable according to the original specifications, you can do. If you have like a 5-day interval, then obviously it's going to be more expensive per unit time. So every 5 days you would be changing out the amount of ethanol, and that's obviously going to be really expensive. So people don't do that, okay? But you might change it out every month, or you might change it out every 3/4 of a month. And if you amortize that cost over all the days, in this case it's 20 days, you get $3,949 per day. There is some cost to this. And what I want to demonstrate here in this plot is that, you know, some people just say, well, look, we don't do that at all. So that's not a cost that we really are concerned about or want to do. And so what I did was I took out that cost altogether and I replotted the plots that we looked at before. Here's the original plot here. You can see there's a crossover time right around 3 months. Now I took the cost of basically reuse out and reuse validation and changing out the solvents. You can see that it improves the situation. I mean, it lowers this slope quite considerably. And then it brings it out, the crossover time, to 8 months. So this slope right here is lowered considerably, and the crossover time is 8 months. You can see that you're improving the situation, but anything after 8 months is going to be more costly for you to operate compared to a CO2 extractor. Now let's focus on energy costs. What we're comparing is this blue line here, which is quite small compared to all these other blocks. Compared to this thin blue line here, you can't even see it. It's right on top. So we're comparing the energy cost for ethanol, which most of it is involved in taking large amounts of ethanol and distilling it off. As opposed to CO2, there is an energy cost. Most of the energy cost here is in refrigeration. So let's get into it. This is a table comparing ethanol energy costs to CO2 energy costs. What we have in the first table is ethanol costs just for the extraction operation only, not the rest of the operation. So this is including evaporation of the ethanol to produce an oil. And what we have there is we have about approximately 114 liters per cycle to be evaporated. You can see the assumptions that we had in the previous slide, 55 cycles per day, 3 units that are being run, 30 pounds per cycle, and 1 gallon per pound of input biomass. And you got 24 kilowatts per liter approximately that you need to have at 9 cents per kilowatt hour. This is what we pay. And here's for 423.22 cost per day. So you can think of heating up the fluid and then adding more energy into it to get it to vaporize. That's called the heat of vaporization. That heat of vaporization is dominating the overall energy requirement. It's really what they talk about when they talk about distillation. So that heat of vaporization really costs you a lot of money. And the more ethanol you have, the larger your operation, the more your energy costs are going to be. And you can kind of use your own numbers in here. If this is double, you can double that number. If you think you have a much better, say you're running at half ton per day, that'd be $223 per day. So those are the things that you can do just in your head easily enough to kind of estimate your own operation in this. Now, this is the CO2 end-to-end energy. It's not only the CO2 process itself, but it's all of the other kilowatts that are required to run the whole entire process. So this is actually including the winterization process, the refrigeration associated with that, and also the distillation from the falling film, the energy required for that. You're looking at approximately $77 per day, as opposed to $423 per day. So there's quite a big difference. And it really has to do with ethanol and that heat of vaporization. It's really having a huge impact on, really how much energy you need. Now, the other thing is some people use cold cryo extraction. And that is not assumed here. I mean, it is cold. I mean, I think it's like at -20 or -30. Some people use, for example, liquid nitrogen. In that case, you are using a solvent, liquid nitrogen, or basically a cooled liquid gas to cool something down. There's a cost associated with that. I haven't really looked at that particular setup in this cost at all. And I'm not even sure if I'd put that in this energy cost. It may be a different operating cost. But we're certainly not talking here about liquid nitrogen refrigeration, which is expensive, by the way. Let's talk a moment about labor. Basically, you have head count, and the head count makes up labor. You can see that I'm assuming that they're the same. And this has to do with just 1 ton per day. If you're running 3 shifts, basically the main part of your labor is basically your duplication of shifts. One thing that you can do is increase your equipment and just reduce or eliminate your second and third shift altogether. And that will improve matters quite a bit. That will actually take this down, down 1/3. And this down 1/3 as well. So there's some assumptions in there. Certainly labor is something that every operation struggles with, I think. Whether you have a trained labor force, people showing up for work, redundancy in your labor, those are things that are really important. And I think that, getting the right people on board is always key in your entire operation. One thing that I would point out is that, hey, look, you can afford some pretty good people on your operating staff. People are going to show up to work. People are going to are professionals. You can afford those guys because your operating costs are quite a little bit less. Even though I have them at the same price, I would just say it's a decent assumption. I think that if you had the idea that ethanol had less labor, I think that is not the case. So FYI on that. But if you really believe that, you can even eliminate it and it won't make any difference because you still have that crossover, and the crossover it's not going to have a huge impact. You're still going to have higher operating costs for ethanol over time, and that's going to increase it's going to decrease your profits, and it's going to decrease your value of your installation and your business. So this is the overall then cost comparison that's more accurate, I think, than just looking at equipment cost and startup costs. If you compare the overall operating costs you can see that you get a much, much different picture. Ethanol won on the first slide, but in this case, you can see that over time, CO2 just completely destroys ethanol from an operating cost standpoint. And so that really has to do with, again, several things. Solvent reuse, solvent loss, the high cost of ethanol as a solvent compared to CO2 in the first place. And then you add those costs up over time and they become dramatically different. You can see that this solution right here actually is the best solution from a cost standpoint. Obviously, this will have a huge impact on your enterprise value. If your goal is to start up a hemp operation, for example, and build it up to a certain level and then sell it or leverage it at the bank or whatever, you're going to need to have profit. What I've done here is I've kind of listed the different things that profit impacts. CO2 extraction facilities at the same level of throughput will generate approximately 10 to 20x cash per period, everything else being equal. That's ceteris paribus. Net present value of CO2 operation will be significantly larger. This has to do with the fact that its costs are significantly less. So everything else being equal, you're going to have a greater net margin. You're going to have a greater cash flow. That cash flow is going to be added up over the number of periods and the number of years that you have and discounted back to today's dollars at a discount rate. It's going to give you a larger number. The multiples also are a very key way that you can think about the value of your company. If I have a company with a EBITDA, say, of 10, and then I have a company with an EBITDA of 1, the multiple that I would be paid for the EBITDA of 10 would be much greater than the multiple of 1 because it's a much more profitable business. Also, something not to ignore is the book value, and that's the basically current assets and long-term assets of the company versus the liabilities. Book value is largely driven by the PPE of a company, and you're paying more for the equipment because it's generating better profits. And so the book value is better. Also, the enterprise value will also go up. So a lot of investors and people who buy companies also look at the enterprise value. Enterprise value is equity plus debt minus cash. And if you run the numbers for a CO2 operation, you'll see that the enterprise value is a lot better. And that basically has to do with EBIT and cash generation. There are a bunch of different ways you can value your company. It all goes down to if your company is generating cash, you're going to have a higher valuation, better multiple. If you've paid more for your equipment, you have more assets on your books, your company's worth more, and your enterprise value will also increase. In this analysis, I also didn't talk about other hidden costs for ethanol extraction. And some of these are applicable and some of them are not, depending on the jurisdiction that you're in and depending on where you're really coming from. But we have seen and have had experience with these items. Number one, hazardous waste disposal costs. If you have, for example, denatured ethanol and you have 5 to 10% that's lost to the biomass, that biomass has to be treated in such a way that it could be considered to be hazardous waste, which makes it very expensive to get rid of. What a lot of people do, and what we have seen, is they warehouse it and they let it outgas. And of course, if you have the denaturant in there, heptane, or if you have hexane in there, or acetone, or IPA, or whatever it is that you have in there, the overall amount that is in that solvent in the biomass actually will go down, but it still kind of hangs out a lot. We had a situation where somebody sold us about 20,000 pounds of biomass, and we went out to test it. And it had a lot of IPA ethanol in it. It had obviously been soaked. It still had 7% of the CBD in it. It's kind of interesting. They were trying to sell that to us, and it had sat in their warehouse for over a year. When we looked at it, we actually determined that it was hazardous waste, and it would have cost us more to dispose of it than to buy it. So that's something you just need to think about. If you're going to let it outgas, there's also hazardous air pollution emissions and permits for that, and those are costly. So you should think about that. Also, increased insurance costs associated with ethanol. For example, we have a 5-ton per day facility here in Wisconsin, and we had our insurance person walk through. We had a tote of ethanol for our winterization process in there, and they were very concerned about that. They were at the point of yanking our insurance. What we ended up doing was we ended up giving them a hazardous analysis plan and a chemical hygiene plan, and that sufficed. You got to realize that there are limits to the amount of ethanol that you can have in your facility, and your insurance company is definitely going to be looking at things like what your occupancy is. Do you have all of those extra things that are required in your building to actually make it safe? Also, adjoining building issues. A lot of people operate in suites. And if you have an ethanol extraction facility and you're operating next to somebody else, you may have issues with that other person. And also the rules associated with offsets. So think about that. You just need to make sure that you are aware that those are some of the issues. And then also local permitting associated with ethanol and flammable solvents, and having a large amount of flammable solvents. It can be difficult in some jurisdictions. One thing that's nice about CO2 is it's an inert gas, and there's an unlimited amount that you can store on your site. There's an unlimited amount that you can have in your building. That's it. And it costs 4 cents a pound instead of $33 per gallon. So it's something you need to think about. So here's a summary of the operating costs and some conclusions for ethanol versus CO2 when it comes to operating costs. You can see on the left-hand column, we have all of our different costs: infrastructure, equipment, operating, enterprise value, throughput, scalability, hidden costs. You can see that we have on the second and third column, the ethanol versus CO2. We already talked about how ethanol equipment is less expensive, so it gets a definite win there. Startup costs are less for ethanol, even with infrastructure. But if you just look at the infrastructure cost alone, CO2 wins. So you can operate in an F2 facility, and you don't have to really do a lot to it. In terms of operating costs, CO2 wins the day, hands down. I think any way you run the numbers, if you plot them out over time, you're definitely going to be a lot less costly running a CO2 facility. And it all comes down to basically power and loss of solvent. And of course, your enterprise value is going to be a lot higher. Throughput, we just kind of made that the basis of our comparison, so there's no win or lose on that. And then scalability, I didn't talk about that in this presentation, but I did talk a little bit about hidden costs. And CO2 really doesn't have those hidden costs that we talked about in the previous slide. So you can see CO2 actually is winning on the overall operating costs. So who gets the checkmate? That's the question.
Hey, thanks for watching. We have many resources available for you to get your hemp operation up and running. Calculators, advanced extraction guides, distillation guides, CBD jam sessions. We have just lots of content. Links to which are in the description below, as well as the cards up above. I'd like to hear from you. What was your favorite part of the video? If you would let me know in the comments below, I'd be really appreciative of it. Also, don't forget to subscribe to our channel for more content like this.